video is about telescopes, the two basic types of telescopes, the three powers of a telescope, and the effect of the atmosphere on light coming from objects beyond Earth. In the lecture outline, the first set of vocabulary terms is about the basic types of telescopes, refractors and reflectors. The second set of terms is about the three powers of telescopes that enable them to extend our vision: the light gathering power, the resolving power, and magnifying power. And the third set of terms is about the effect of the atmosphere on starlight. Let's start with the two basic types of telescopes. The first type of telescope built was the refractor telescope, which uses a glass lens at the front of the telescope for its objective, that is, its main optical element. The glass lens is what gathers and focuses the light. Light is refracted or bent as it passes through the lens. The two photos show the largest refractor telescope ever built, the 40-inch refractor at the Yerkes Observatory, 50 miles outside of Chicago, which was built way back in the 1890s. No larger refractor has ever been built because of the disadvantages of making really large refractors. By the way, when we talk about the size of a telescope, we use the diameter of the objective, not the length of the tube. We'll see later that it is the diameter of the objective that determines how much the telescope extends the power of our vision. The first disadvantage of a refractor telescope is an effect called chromatic aberration, or color distortion, that is caused by different colors of light focusing to different points behind the objective. A rainbow of colors is produced around the image. You can reduce the chromatic aberration by making the telescope have a really long focal length, which is illustrated well by the Yerkes refractor that is over 60 feet long, while the objective aperture is just 40 inches in diameter. Another way to reduce the chromatic aberration is to use multiple lenses made of special types of glass cemented together to get all of the visible wavelengths focused at the same spot. This increases the cost a lot. Another significant disadvantage is that the support for the objective, the glass lens, is just along the perimeter, which means the glass lens can sag slightly because of its weight. A lens larger than 20 inches in diameter is going to weigh a lot, and because we're dealing with the very tiny wavelengths of visible optical light, it won't take much sagging to distort the images. Finally, because the light has to pass through the glass lens, the front and back sides need to be perfectly shaped, and the inside of the lens must be perfectly uniform as well. All this means that it would be prohibitively expensive to build anything larger than the Yerkes 40-inch refractor. Now, on smaller scales, it makes a lot of sense to build a small refractor telescope because they can be very sturdy and won't get the objective and eyepiece out of alignment, and the inside of the tube is sealed off from the elements. That's why a rifle scope or spyglass are refractors. However, we'll see in the next slide, research telescopes need to be built as large as possible. About 3/4 of a century after the refractor telescope was invented, the second type of telescope, the reflector telescope, was invented by Isaac Newton. The line art schematics show you the three common light paths for a reflector telescope. With a reflector telescope, the light passes down the tube of the telescope to hit a curved mirror, which is the objective, at the back end of the telescope. Many of the telescopes you see at a public star party by the local astronomy club are the Newtonian design, where the light then bounces back up the tube to hit a flat diagonal mirror, which redirects the light to an eyepiece near the top of the telescope. Another popular design you'll see at the star party is the Cassegrain design that has the light bounce off the objective mirror, go all the way back up the tube to a curved secondary mirror, which then redirects the light back down all the way through a hole in the primary mirror to an eyepiece or detector at the back end of the telescope. This collapses the light path to make the Cassegrain reflector telescopes very compact. Reflectors have some advantages over refractors. Because light is reflecting off a mirror, not refracting, passing through a lens, there is no chromatic aberration. The support for the primary mirror at the back end of the telescope is all along the back side of the mirror, so there's no sagging of the mirror, and they can be made very large.
Because light is bouncing off the front side of the mirror, only one side of the primary and secondary mirrors must be perfect. This means a large reflector telescope is going to be much cheaper to build than a refractor. All modern research telescopes are reflectors. This is a picture of the Hale 200-inch telescope at Palomar Observatory outside of San Diego. It has a primary mirror 200 inches, or 5 meters in diameter, and it was the largest optical or visible light telescope in the world for several decades in the 20th century. Now, the large optical telescopes have primary mirrors 8 to 10 meters across. In the future, optical telescopes with objectives 30 or more meters across will be built. The Hubble Space Telescope is a reflector telescope in orbit well above the Earth's atmosphere. Click on the picture to bring up the HST slide. Here's a cutaway drawing of Hubble. Hubble uses a Cassegrain light path, so light enters the top of the telescope, where the aperture door is, goes down the tube, and reflects off the primary mirror colored orange in the drawing. It is 2.4 meters across. The light then bounces off the secondary mirror and travels back down the tube through a hole in the primary mirror to a bunch of different cameras and spectrometers colored purple in the drawing. Unfortunately, the primary mirror suffers from something called spherical aberration, which means the objective, the primary mirror, is not exactly parabolic but shaped more like a piece of a sphere, so not all the light is focused to the same point. This made the images fuzzier, blurrier than they should be. The primary mirror is flat by 2 microns, or about 1/50th the width of a human hair. Before the problem was fixed, Hubble was still able to produce images sharper than what could be done from the ground. The spherical aberration was fixed by using corrective optics to perfectly focus the light on the cameras and spectrometers. Fortunately, the defect in the primary mirror was a textbook case of spherical aberration, so we could correct the perfect mistake into perfect images.